We are finally ready to talk about some calculus, and this first lesson is going to give you an introduction to derivatives. And believe it or not, it's pretty simple. For many years, you have been taught or have learned about linear functions. So here I have a nice line. And we talked about an important feature of that line would be the slope. So the slope at this point here, let's say, is m. And the slope here is also m. So no matter where you pick on this line, the slope is always the same. It's a constant slope. And we talk about slope as a rise over a run to give us the slope. But obviously not all curves are linear. So for instance, this curvy function here, well, the slope is not always the same, but we can still talk about the concept of slope. So we have a slope here, which is different than the slope here, which is different from the slope here, so on and so forth. And so in calculus, we talk about what is the slope of the curve at different points along a non-linear function, or possibly a linear function, and that's the idea of a derivative, is to find the slope. In context, a slope is an instantaneous rate of change, or emphasize the word rate of change. Again, back to the linear, the rate of change is always the same. Let's just say 5 miles an hour as an example. Well, here, at this point here, the instantaneous rate of change may be 5 miles an hour, but here the instantaneous rate of change might only be 1, and down here it might be -2. One of the ways we try to represent the instant slope or the instantaneous rate of change is to draw a tangent to the curve. So in this case here, if I drew a tangent, the slope of this tangent line would be equivalent to the instantaneous rate of change of the function at this particular point. So if I found this tangent line's slope, that would give us the instantaneous rate of change at this point. And that can be chosen anywhere. If I drew a tangent line for this point here, I'm just going to draw a real small and local. It's touching, in theory, locally, just touching at one point. The slope of that line is, again, the instantaneous rate of change of the function, or the slope of the function at a particular point, and the slope constantly changes. In this function here, we have, looks like the behavior is a little bit different once we get to the left or right of this point x equals a, but we can compute the slope. So the slope here would be m. Let's say it's 5, and then the slope here is also 5 and 5 and 5 and 5. That's great. On the right-hand side, well, perhaps this slope is 5, but then this one is 1. The slope here might be 0, and the slope here might be -2. My question to you now is, what is the slope right here? And what we would say is this is, so to speak, confused because on the left-hand side, the slope looks like it's approaching maybe 5, but on the right-hand side, the slope might be -6, and there's a confusion at this point. And so at these corners, the technical name, believe it or not, is a corner, at these sharp transitions or corners, we say that the function does not have a slope. And in terms of derivatives, we'll learn later, we'll say the function is not differentiable at the point x equals a. But for now, we're going to just stick with slope. This function does not have a slope because we have a corner. Corner is just a sharp transition within the function. And this graph here, well, looks like we have another sharp transition, another corner. So at this point, at this value x equals a, the function does not have a slope. Over here, the slope changes. Notice here as I move closer to that point, the slope is getting steeper and steeper and steeper, larger, larger, and you might argue that the slope is increasing without bound. There's the potential that the slope is approaching infinity from the left. From the right-hand side, the slope, well, it's a negative number, then that's more negative. Negative, very, very large in magnitude, getting more and more negative, and so that one looks like it's approaching maybe negative infinity. And in the event that it would approach these behaviors of infinity, negative infinity, one positive infinity, one negative infinity, then we get this thing called a cusp. But a cusp is just essentially an extreme corner. But at any rate, there is no slope when we have a corner or a cusp. There is no derivative, there is no slope, there's no instantaneous rate of change. Those words will start to resonate as equivalent in your mind. Slope, instantaneous rate of change, derivative at x equals a. So this particular function does not have a slope at that point. We could also say it doesn't have a unique tangent. Depending on how you're defining tangent here, well, I could draw a tangent that goes to that point and only that point, but I could draw another tangent here that goes to that point and only that point, and none of these tangents slope accurately tell us the instantaneous rate of change or slope at that sharp corner. This next graph, I'm going to attempt to draw two semicircles. I can't guarantee they'll be great, but there's one semicircle, and then the other semicircles picks up from this. This is a continuous curve, and then goes like that. My attempt was to draw two semicircles. Whether or not I did it, I don't know. In fact, as I look at my drawing, I'm certain I didn't draw it the way I exactly wanted it. But in this particular case, if I were to draw two perfect semicircles, the tangent line, there actually is a tangent line, but the tangent line here would be vertical, so it has a unique tangent line, but you would notice that the slope of that would be undefined, and so we would say that it does not have a slope. Where you have a vertical line tangent, you would say it doesn't have an instantaneous rate of change. So that one's a little bit different than a corner. Okay. This next function, well, we have a bunch of defined slopes. They're changing, but they're defined. Over here, we have a bunch of defined slopes. But you would notice at x equals a, well, this function is not even continuous, and when the function's not continuous, we can't determine what the slope will be at that point because we have this jump here, and the math of it confuses it, and we say then that the function does not have a slope when it's not continuous. And that could be true if the function did something like this with a hole, a removable discontinuity. We would also say that at the point x equals a here, this function does not have a slope. So if the function is not continuous, then the function does not have a slope at x equals a. In the case of an asymptote, well, clearly, let's say the asymptote occurs at x equals a. In the case of an asymptote, the function does not have a slope at that point. In fact, the function is not even defined. So to have a slope, the function has to be defined, the function has to be continuous, and then at that point, you can do some math, which is going to be the purpose of this lesson, is to determine the math to decide. Let me draw this function here. The math is going to be used to decide what the slope will be of a curve that's not linear. You can use the formulas with linear, but the idea behind the derivative math or theory or definition or concept is to come up with an equation to find the slope. And that's it. I mean, it's fairly simple. Calculus comes down to two things, derivatives and antiderivatives. And derivatives are simply slopes. And I want you to understand this big picture. We're about to do some really heavy math, and we're going to grind out some equations. We're going to get into some theory, but don't lose sight of that idea that a derivative is simply a slope. And in moments here, we are going to use this idea to represent the slope by drawing a tangent and figuring out the slope of the tangent. So if I was able to come up with the number for the slope of that tangent, well, then that would be the derivative or the slope of the function. Same thing here. Tangent, slope of the tangent gives me the instantaneous rate of change. It gives me the slope. It gives me the derivative at a particular x value.